We're going to switch gears now and move out into the magnetosphere. Dr. Lyons will talk on particle acceleration by plasma turbulence.
Now, much work has been done on the pitch angle diffusion of radiation belt particles, which results from resonant interactions with plasma waves. And most of this work is valid for cyclotron interactions with waves of frequencies much less than the gyro frequencies of the resonant particles, since in this case energy diffusion is negligible. However, when the frequencies of the waves are not much less than the gyro frequency, energy diffusion occurs at rates that are comparable to pitch angle diffusion rates. Now, I'd like to discuss general relations for energy and pitch angle diffusion resulting from resonant interactions with waves of any frequency. The relations are valid for any mode of weak plasma turbulence, providing the plasma is homogeneous on the scale of one wavelength. While I will be later in the talk applying these relations to the radiation belts and to the resulting precipitation of auroral particles, the relations are applicable to other plasmas such as the ionosphere and the solar wind. This first slide shows the basic approach and results of the analysis. We start with the general quasi-linear diffusion equation of Kendall and Engelmann, which gives the changes in the zeroth order particle distribution function, which results from a distribution of waves which is describable by linear theory. So by algebraically manipulating the terms of the equation, it can be put into the form of a diffusion equation in spherical coordinates. F is the distribution function, standard diffusion equation written in spherical coordinates. D alpha alpha is pitch angle diffusion that helps. D alpha alpha is the pitch angle diffusion coefficients, which gives the diffusion in pitch angle resulting from gradients of the distribution function in pitch angle. DVV is the speed diffusion coefficient, which gives the diffusion in speed resulting from gradients of the distribution function in speed. And D alpha V and dV alpha are the mixed diffusion coefficients, which give the diffusion in pitch angle and speed, resulting from gradients in speed and pitch angle, respectively. Each diffusion coefficient can be written as a sum over the resonant number n and an integral over the perpendicular wave number k perp. The integral over k perp allows for the spread of wave energy with wave normal angle. And the sum over n allows for all the resonant interactions, n equals 0 being the Landau resonance, and the other values of n being the cyclotron harmonic resonances. Now, the pitch angle diffusion coefficient for a given n and k perp is a rather complicated function of the particle velocity and the wave distribution evaluated at the resonant value of k parallel, where the resonant value of k parallel is given by the dispersion relationship with the wave frequency being a function of the wave vector. Now, once the pitch angle diffusion coefficient is obtained, the mixed diffusion coefficients, d alpha v and dv alpha, can be obtained from the pitch angle diffusion coefficient by multiplying by this extremely simple factor, and the speed diffusion coefficients are obtained by simply multiplying by the same factor squared. So that once you've calculated the pitch angle diffusion coefficient, all the elements of the diffusion matrix can be attained by simple multiplications. And you can see from this relation that for small wave frequencies with respect to the gyro frequency of the resonant particle, that the pitch angle diffusion coefficient becomes the dominant diffusion coefficient. Now, these same relations can be obtained by a few simple physical arguments. Now, from a few simple quantum mechanical arguments, we find that a particle interacting with a single wave is constrained to move along circular diffusion surfaces centered at the parallel phase velocity along the v parallel axis. Now, if we differentiate this equation and use the resonance condition, we relate the incremental change in speed to the incremental change in pitch angle during a wave-particle interaction, and we end up with the same relationships that we had before between the elements of the diffusion matrix. So while calculating the pitch angle diffusion coefficient may be complicated, determining the diffusion coefficients which are necessary to evaluate energy diffusion rates is very simple once you have the pitch angle diffusion coefficient. And to apply this analysis to trapped particles in the Earth's dipole field, we must average the diffusion equation over the bounce orbit of particles. The next slide here gives a result. You get a bounce orbit averaged diffusion coefficient in equatorial pitch angle and speed, where the diffusion coefficients are written as integrals from the geomagnetic equator to the particle's mirror latitude. I've applied these relations to Wistner mode waves and ion cyclotron waves, but I haven't obtained any new conclusions of magnetospheric interest. However, I'd like to discuss some results which I've obtained from applying these relations to the intense electrostatic waves that have been observed on auroral lines of force, basically in the equatorial region by Kennel, Scar, Fredericks, and Coroniti. These waves have a frequency near 3/2 the local electron gyro frequency, and it's been suggested that these waves are responsible for the diffusion of auroral electrons at energies of 1/10 to about 10 keV, energies which are too low for interactions with Wistner mode waves. So here I've plotted the pitch angle and speed diffusion coefficients for interactions with these waves, assuming the waves are at L equals 7. Diffusion coefficients are normalized to the square of the wave amplitude and the thermal energy, and they're plotted as a function of equatorial pitch angle for energies normalized to the thermal energy of plasma sheet electrons being on the order of keV or so. I want to point out that the diffusion coefficients maximize in general near the thermal energy, and that for energies less than about 10 times the thermal energy, speed diffusion occurs at rates comparable to pitch angle diffusion, but at higher energies the speed diffusion rates fall off with respect to the pitch angle diffusion rates. That the speed diffusion coefficient never greatly exceeds the pitch angle diffusion coefficient doesn't rule out the possibility of significant electron energization, since in strong pitch angle diffusion the loss rate becomes limited by the size of the loss cone. Energy diffusion rates can be much greater than the actual particle loss rates. So using these calculated diffusion coefficients, I find that electrons from a few tenths to a few keV should be put on strong diffusion by the typical wave amplitudes which are observed, with typical amplitudes being 1 to 10 millivolts per meter, and that waves of the largest observed amplitude, which is approximately 100 millivolts per meter, these waves can cause strong diffusion for electrons up to 100 keV, which implies, in fact, that you can get a significant acceleration to energies above 100 keV. I'd like to switch to auroral precipitation and correlations with these waves. Now, Whalen and McDermott have reported sounding rocket observations of electron energy spectra at 2 local pitch angles within the loss cone, which they obtained during a post-breakup aurora. This slide shows the observed energy spectra at 2 pitch angles, 76 degrees and 42 degrees. Notice there's generally pitch angle isotropy up to a few keV, in this case 5 keV, with a gradually increasing anisotropy at higher energies. To explain this type of pitch angle dependence of the energy spectra, we need waves that will cause diffusion most strongly at energies near a keV or so, and then gradually decreasing diffusion rates at higher energies. So what I did was I first drew smooth curves through the 2 energy spectra. The 76 degree smooth curve that I drew is shown. The 42 degree curve is not. Then at energies above about 5 keV, where the fluxes are anisotropic, I use the ratio of the fluxes of the 2 pitch angles to obtain the pitch angle diffusion coefficient at the edge of the loss cone as a function of energy. This is the solid line extending from 5 to 20 keV in the upper part of the figure here. Now, by adjusting the wave amplitude and the thermal energy for the particles responsible for these electrostatic waves, I found that if we choose a wave amplitude of 1.7 millivolts per meter and a thermal energy of about 2 keV, that the diffusion coefficients calculated for interactions with the electrostatic waves agree quite well with the experimentally determined diffusion coefficients. So finally, using the theoretical diffusion coefficients, I went back and calculated the ratio at the 2 pitch angles, and that's the dashed line here through the 42 degree energy spectrum. That such good agreement is obtained, in fact almost embarrassingly good. I don't believe that its theory is that good. This suggests that electron diffusion, at least at the time of this rocket flight, resulted from interactions with electrostatic waves. And this suggests that at least at times diffuse auroral electron precipitation may be caused by these interactions, which pitch angle scatter electrons out of a trapped particle reservoir. Certainly, more observations are required to determine just how general a case this may be. And it's, of course, highly unlikely that interactions with these waves are responsible for auroral arcs or for the dynamic activity associated with breakups. I'd like to make a few comments about electron acceleration near the outer boundary of the radiation belts. Now, as a result of an extensive review of electron data near the outer boundary, Kennel concluded that electrons from below 1 keV to near 100 keV approach pitch angle isotropy inside and near the loss cone. This is near the outer boundary of the radiation belts. And he suggested that the energy diffusion, which is associated with the required strong pitch angle diffusion, may be responsible for accelerating electrons up to energies of at least a few tens of keV. Now, for the electrostatic waves that I'm discussing here to cause strong diffusion up to, say, 100 keV, wave amplitudes of at least 50 millivolts per meter are required. For example, I chose a wave amplitude of 100 millivolts per meter, which is the largest amplitude they observed. The time scale for speed diffusion for a 40 keV electron is 100 seconds, which is well below the minimum lifetime of 40 keV electrons at L equals 7, which is 600 seconds. To determine whether the electrostatic waves are indeed responsible for strong pitch angle diffusion and energization to energies above 40 keV will require correlated wave and particle measurements. Specifically, wave amplitudes approaching 100 millivolts per meter are required near the outer boundary of the radiation belts. Waves of such intensity would not be expected, well, they should be somewhat localized and would not extend far within the outer boundary. Young et al. Have pointed out that the wave intensity will be closely related to the amount of free energy which is associated with a peak in the perpendicular electron distribution function, and that a small amount of cold plasma is required to initiate the instability. Thus, the wave intensity should be strongest when incoming plasma sheet electrons first encounter some cold plasma, and as the plasma is transported further inward, energy diffusion will smooth out the peak in the distribution function, thus reducing the free energy available for the unstable waves. So in conclusion, electron diffusion driven by the electrostatic waves appears to be a likely source of diffuse auroral precipitation and perhaps a possibly important source for the acceleration of radiation belt electrons.
Your last slide is a very consistent with what S cube observing this pitch angle dependence.
With what's
But
that?
L value is around 5. Your calculation is 8. And your calculation is outside the plasma sphere.
Oh, this is all outside the plasma sphere. This is
Yeah.
on auroral lines of force.
Yeah. So, but what I thought was you are considering electrostatic waves.
Yes,
But
electrostatic.
how about the Whistler mode type?
The Whistler mode waves, at least the ones that I've seen that are observed, wouldn't interact with these particles at all. They interact with higher energy particles. And
Yeah, I have several data which I would like to show you.
okay, very good.
This is a tangential comment. You may comment or respond to it or not as you please, but just as a point of information, we do see Whistler-triggered emissions, which we interpret as evidence of strong pitch angle diffusion, and we usually give energies of the order of 30 kilovolts as the particles interact with the Whistler waves. However, we less often, but significantly, we do observe Whistler-triggered emissions at frequencies well below the usual triggering frequency, which is half the electron gyro frequency. And if the same interpretation is applied, then this would be strong pitch angle diffusion taking place with higher energy particles. So you might regard 30 kilovolts as a lower energy for strong pitch angle diffusion in the Whistler mode, but it can operate at higher energies if one model is applicable to all Whistler wave particle interactions.
Yeah, I certainly agree that Whistler mode waves could cause strong diffusion at energies above 40 keV, but there's little evidence of any that with similar ways could possibly explain the precipitation of the diffuse auroral electron precipitation, which occurs here in the vicinity of 1 keV.
Yeah, I had a question on the same line, and that is that it seems as though you need an acceleration mechanism which can accelerate electrons up to MeV energies, and I wanted to know whether you could give me an estimate of what time scale these particular waves would require to do such an acceleration, and also whether you'd expect the particles to remain trapped, or would they just be diffused out of the radiation belts within that time scale
I think I'd
by
like
pitch angle scattering loss?
like to refrain answering that question until I've managed to solve the two-dimensional diffusion equation to see whether indeed you do get significant energization up to an MeV. It seems possible that since you do have acceleration up to those energies, that some particles could get diffused, but there you're not on strong diffusion, and the pitch angle diffusion rates are far greater. So it's going to be touchy as to whether it can get particles to an MeV or not.
Yeah. Also, have you looked at the analogous problem for protons? Because they too, when you just cross the outer boundary of trapping, are subject to strong pitch angle scattering up to energies of at least several hundred keV.
Yeah, apparently, I guess plasma sheet type protons undergo the same type of behavior, becoming isotropic in the same general vicinity. And I guess the work by Ferd Coroniti indicates strong wave turbulence can be initiated, so that I would imagine that this wave turbulence for the protons would be similarly responsible for the acceleration of protons to radiation belt type energies.